Alright guys, so for our next project, we are going to be making an electric guitar body. Very, very popular CNC project, actually my first real CNC project that I ever made, and we're going to be making the entire body from scratch with all the features so we can actually put in all the electric guitar components and then go through all of the computer-aided manufacturing steps so you can actually reproduce it in real life. Now before we get started on all of the design portion or all of the cam portion, we may as well kind of go over all of the terminologies about all the components that you can find within an electric guitar body, because this will help us a lot when we decide to categorize and organize all of the operations that we do during all of our tool paths. So if I say, let's do the neck before we do the pickups, then you guys will actually know what we're talking about. That being said, I am not a guitarist by any means, so if I get any of these terminologies wrong, well, just don't believe me for any of them. Up at the top of the guitar, we have this little recess for our neck to go into, and we also have 4 holes that we can pass some bolts or some screws through the body and go into the neck of the guitar. Just below that, we have got 2 cavities right here. This is for a thing called a pickup. Now, pickup is basically just a really thin copper wire, about 4 kilometers sometimes, wrapped round and round and around an electromagnet, so that when you actually start to pluck a guitar string, that frequency generates a very small amount of current that the pickup can pick up. That signal is then amplified through an amp, and then you get rock and roll out the other end. Usually they're all this kind of funky, weird, kind of blocky with old step over kind of shape, but they'll all fit in this little section. These are exactly the same size. On a lot of guitars you'll have 2, sometimes 3, but they're usually always this kind of strange shape. Just below it we have a little slot that cuts all the way through for something known as a bridge, and then just above it we have got 6 mounting holes. This is going to be used for 6 screws to actually screw into that, and that will hold down all of the strings when they're in such a pretty intense amount of tension. Just below that we have got 2 holes for some potentiometers. These are the knobs where you can adjust the volume or anything like that. And then just below that we have got 2 more mounting holes, and then this very, very skinny slot. This is where you'll have a 3-point lever that goes in between it, where you want to utilize both pickups, just one pickup or the other pickup. And from that you'll get different sounds that come out of it. On the other side, we have got this really nice kind of angled chamfer that actually goes with the curved profile of our guitar. This just makes it a little bit more comfortable to hold when you're playing it. But a lot of people have these on all different corners, all the internal and external corners of their guitar. We've just put it over here just so we can have one as an example. This will be a genuinely tricky area for the cam. And then flipping over to the underside of our guitar, as you can see, our holes do pass all the way through on the neck. Our bridge will be passing all the way through, but more importantly, we have got this kind of teardrop shaped cavity in the back. This shape of the cavity can really be any shape you would like. It can be boxy, circular, doesn't really matter. We've kind of modeled this, so it kind of follows the profile of this outer guitar section, and then it's just been mirrored across a horizontal line. But this is basically just to house in all of the ugly wires and electronics and all the wires coming out of the potentiometers, just kind of hold it in place. As you can see, there is a little step down right here where you can have a backer plate, and then you've got 3 holes where that backer plate can be screwed down. But other than that, a guitar body that you could make on a CNC is tremendously simple. Not that many parts to it. There are some features on it that you'll find in more finished guitars that we won't be making on this CNC. For example, if you look at it from a top-down perspective, there should be a hole right here for a big metal rod that runs through the neck and actually goes into the body. That's because when you are putting all of your tension on all of your strings, that's a tremendous amount of force, and it'll actually cause the neck to start to bow upwards. So you need a big metal rod to kind of stiffen everything in place. Furthermore, you'll also need to have a hole going in that way, so you can actually plug in your jack cord, which will turn this into an electric guitar and not just a complicated bit of wooden block. But other than that, pretty simple. So let's go ahead and close this down and start with a brand new file. So we'll start off by double checking that our document settings are going to be changed from inches over to millimeters. A lot of guitars that came out during the 1970s and sometimes into the 80s were made in Japan. They were these really fantastic recreations of guitars that were popular in the 1950s, and they were all made in millimeters, hence we are going to be designing in millimeters. Those guitars that were produced by Japan were incredibly important to the history of rock and roll. That kind of spurred on the 70s and the 80s punk scene, rock and roll scene. So if you love any rock and roll bands that came out of the 80s, which I think is most of us, you can thank Japanese guitars for that. They really were absolutely essential in the rock and roll scene. Because of that, we are going to be making our profile based on one of those Japanese guitars. So we're going to be importing an image and then tracing around it with a fit point spline, just like we did for the football in the appearance episodes. So go ahead and go into your insert menu, click canvases, and we're going to be inserting an image from your computer. You can find this image on our website. So with this image selected, we are going to be placing it on the top plane. Remember, we're always wanting to have a top-down view anytime we're doing any cam operations, because that's the direction that the tool bit is going to be looking down. So let's click top on our view cube and get a little bit of a better view. You'll notice that the guitar is kind of tilted off at an angle. We found that rotating this about negative 8.5 degrees lines up all the strings with this grid system behind it. That's just about close enough. And we can click OK to finish that off. We do need to go back into our browser and expand the canvases and then right click our image because we would like to calibrate it. There's really no standard as far as how large guitars should be. Some of them are tiny, like ukulele size. For travel, some of them are absolutely gigantic for big stages. But generally for a guitar like this, something kind of like a Fender, the width would be about 320 millimeters. So luckily we have this kind of grid line that runs just about through its widest section at the bottom. So I'm going to be using my cursor to click on that cross right there and then moving over and selecting the other extreme point right there. And this wants to be 320 millimeters. Now to make the fit point spline, it's usually a lot easier to kind of go around and analyze the shape of our guitar and kind of say, hey, where are some points of interest? And on a really curvy bit of material like this, it's usually going to be a lot easier to put in a bunch of points at the low point and the high point of all of the curves that make up the guitar body, fix them in place so they don't move, and then draw a spline to go around it. So with that being said, let's go ahead and make a brand new sketch on that front plane. Before we get started, you will notice that the origin is not in a convenient location. It's just kind of in the middle of our guitar, and that's because we don't care at all. All of the geometries that we're going to be making are basically built on this top horizontal edge right there, and everything will be kind of made lower and lower and lower and then off of each other. So don't worry about positioning the guitar in any specific location. So we'll start off by using our point tool, and I'm going to be zooming in on the neck, and I'm going to be clicking this top point right there, moving over horizontally so you can see that blue checkered line, clicking once more, going down vertically this time, and then clicking again. These 3 points are going to end up being joined with some lines, and that's going to be a really important harsh angle to work with. But other than that, using your point tool still, I want you guys to go around and click the lowest point and then the highest point all the way around this guitar. It is always a good idea anytime you're using a fit point spline to use the fewest amount of points as possible. It's really easy to think, oh, well, the more points that I put on it, the more accurate it's going to be. And it's just not true at all. You just end up getting a bunch of really tricky, complicated mathematical curves that just end up intersecting with each other, and it's just kind of a pain. So like I said, bottom of all of these curves and the top of all these curves. I'm just going to go ahead and fix this one real quick, pull it in, and that looks good. So we've got quite a few points on there. I'm going to highlight all of them, and then using the fix constraint, do that, and that way we get all of these green points all the way around it. That's going to be perfect for our fit point spline. To start off all this curve, I'm actually going to be using our line tool to join up these top two lines, going over horizontally and then down vertically. Perfect. Now let's go into our create menu, go into spline, fit point spline. And then starting from that bottom point, I'm just going to be going around and clicking all of our green points. Don't worry about making sure this looks absolutely spot on right now. There is no need. It's always going to look a little funky right at the very beginning. But we'll be working successively to make this more and more a guitar-y kind of looking shape. Just like always, anytime you are done with the spline tool, do not hit enter. You want to move your cursor over to this little green check mark to hit OK. Then we can hit escape. Now, if you look at the profile right now, you can see that our fit point spline really does not follow the shape of the guitar at all. And this is why we're going to be having a bit of an iterative approach to our spline work, where we're going to be starting on one of these points and moving this little green angled line. We can adjust the length of this line, the angle, all of that, until it just starts to match that guitar profile. It doesn't need to be perfect. We're going to be doing this a few times. And as soon as that curve looks pretty good, then we can click on the next point. And again, maneuvering this line, changing the angle, and just kind of playing around with it. If it doesn't look quite right, that's fine. Move on to the next point. We're going to be doing this a couple times until it looks about right. So if this doesn't look right on the money, not a big deal whatsoever. So go ahead and go around the entire shape, maybe 2 or 3 times until the profile looks exactly how you want it to look. All right, so after going round the entire profile 2 times, the line actually matches up pretty close with our guitar body. So I'm going to be highlighting the whole thing, hitting our fix icon so nothing moves on us without us telling it so, and we can hit finish sketch. Now we've got a profile that we can extrude upwards 45 millimeters. That is a rough standard about the thickness of guitars, even though the actual shape and length of it can change quite dramatically. We really don't need this canvas anymore, so I'm going to go into the browser and turn it off. Alright, so let's start by making a new sketch on the top plane, and we're going to be making the little recess for the neck to go in. Now I know it looks just like a perfectly rectangular cutout, but there's actually just a little bit of a taper in there. It's a really funky number, 1.8 degrees. I don't know why it's that kind of strange number, but there you go. So we're going to be making, with our line tool, kind of an upside down trapezoid. So we'll be starting off at this top left corner, going down at kind of a dramatic angle, totally horizontal, and then up to that top right corner. We also want to use our line tool again to make this kind of directly symmetrical vertical construction line. So go ahead and move your cursor over until you see that little triangle icon. There we go, that denotes the midpoint. Then going directly downwards until we click that bottom point right there. Perfect. This line, I want it to be absolutely vertical, and it already is, great. But we also want to make this a construction line so these 2 angles can be symmetric. So using our symmetric tool, I'm going to be clicking one line, then the other, and then the construction line. This will make it perfectly symmetric. The total length of this pipe wants to be about 76 millimeters, and the angle between these 2 lines wants to be 1.8 degrees. Kind of funky. We also want to be adding on some 5mm fillets to either of these edges. 5mm, perfect. Then we can just hit finish sketch. Then getting more of a 3-dimensional view, we want to extrude this negative 18mm downwards. We also want to be making some of the 4 holes in this section, so let's make a new sketch on that flat portion. Again, I want to be making that little symmetric vertical construction line again, because we do want all 4 holes to be symmetric about this center line. To do that, we actually only need to make 2 of these holes, and those can be totally the exact same diameter, and they can also be right on top of each other using the vertical constraint. And you guys can find all of the sketch dimensions in our packet. Alright, great, so all of these are in place. Now we can be using our mirror tool, and we want to select both circles, and then selecting that little construction line as our mirror line, and then click OK. We can finish this sketch and then extrude all 4 of those circles right the way through our guitar body. You can do this in a bunch of ways. We've done this lots of times. You can drag the arrow and pull it all the way downwards. You can set the extent type to all, any which way, as long as when you're done, you can see right the way through this guitar body. You'll notice that on this guitar body, we do have some kind of sharp corners there and there. In fact, this corner may not line up exactly perfectly with this top line. If that's the issue, no worries. We can always add in a nice big fillet just to knock that down. So I'm going to be clicking on these 2 bottom lines and adding in an 8mm radius, and this will kind of knock off that sharp point just a little bit. Now, a lot of times guitar bodies, even though they look really lovely and shiny and painted, they're usually made of a really lightweight wood inside. Something like ash or pine or bamboo is very popular. Let's add in some bamboo. That always looks kind of cool. So let's go into wood under our appearance, and then click and drag on a bamboo, and then let's change around the scale of the bamboo just to make it look a little bit more accurate. There we go. Funnily enough, bamboo is not actually a wood, it's actually a grass, which is kind of funky. In the same way that a palm tree is technically not a tree, it's actually a grass that just kind of got out of control. Alright, so let's start out with making one of the pickups, and we're going to be making a new sketch on the very top of our guitar. Again, we're going to be making a vertical construction line, this time from the bottom of our neck, going right the way downwards, and we can make this a construction line. And then using our line tool, we're going to be starting from the bottom and kind of making this strange stepped shape. There we go. We do want to go in with our equal tool and make sure that these 2 collinear lines are equal, and we can also make them collinear. Great. So when we move one, the other should move with it in the exact same way. So using our dimension tool, we're going to say that the top of the pickup is 9.7mm below our neckline. We can also say that the length from that construction wall to that outer edge is 43.5mm. And if these kind of move over, remember, you can always just pull it back in. And then again, using our dimension tool, we'll say that this outer vertical line is 14mm tall, while the other vertical lines are 13.5mm, and the length of this bottom section is 36mm. Perfect. Then we can just go ahead and mirror the sketch. So let's highlight all of our pieces and then select our mirror line as that construction line and click OK. Great, so let's finish that sketch, and then I want to extrude this profile downwards -25mm. And these sharp corners, these aren't going to be able to be, or the internal corners aren't going to be reproduced as we know, so let's round over some of these. So I'm going to be putting in a 4mm radius on all of these internal and external corners, and I'll show you guys a little trick. So we can obviously click all of these outer lines relatively easily, no problem. But if you actually move your cursor, you can click through your piece, which is always really handy. If you kind of know what you're looking for, this will speed up a lot of time. It means that you don't have to move your camera in and out of the way. It's just really, really fast. Like I said, these are going to be a 4mm radii, and click OK, and that'll solve that. And because just one pickup isn't tremendously useful on an electric guitar, we want to make another one that is 100.5mm below. So that's kind of calling for a linear pattern. So let's go into our Create menu, go Pattern, Rectangular Pattern, and then for our type, we actually want to do both the features of the extrusion and the fillet. So let's change that over to Features. And then in our timeline, like I said, let's click on the extrusion and the fillet. For our directions, we can actually click on any of these vertical lines, or lines that are parallel to our green y-axis. So you may as well click the green y-axis. There we go. We can drag this arrow downwards. We really only need 2 of these. Like I said, the extent is going to be 100.5mm. Next on, we are going to be making a little slot cutout, which will be used for our bridge, and then these 6 holes that will live just below our bottom pickup. So let's make a new sketch on that top plane, and we're going to be going into our Create menu, Slot, and then Overall Slot. And I'm just going to be making a general line and then expanding it out to make that slot. With our dimension tool, we can say that it will be located 28mm. 28 millimeters below our pickup. It is going to be a total length of 79 millimeters, and it's going to have a diameter or a width of 17.4 millimeters. Again, we can also put in some points that live on the midpoint of our slot and on the midpoint of our pickup. And as long as you make these 2 points absolutely vertically constrained, it'll centralize it quite well. So next off, we'll be making our 6 holes that live right in between our bridge and our pickup. This is going to be a lot easier if we add just a single circle, dimension it so it's in the right location, and then make a linear pattern of 6 of them, and then make it symmetric about the middle. So let's click C for circle, and this is going to be a 2 millimeter circle, quite small, but it will live 12.7 millimeters up from that bridge. Then we'll go into our create menu, select our rectangular pattern, and select our circle. We want the entire extent of these to be negative 56.4 millimeters, and we would like 6 of them. So we can just click OK, and you'll notice that we do have 6 holes, but they kind of are not limited left or right. So let's make them perfectly stationary. So I want to be making a construction line that joins the middle 2, and this can be done in lots and lots of different ways, but I'm just going to be adding a center point between these 2 lines so that we can add a vertical constraint between these 2 points. There we go. Now all of our circles should be fully constrained, and we can say finish sketch. Now to work on the extrusions of this, our holes are actually only going to be extruded in negative 15 millimeters. But our bridge slot is actually going to be extruded all the way through. So we have to do this in 2 separate commands. Like I said, negative 15 millimeters for our holes, and then we can turn on our sketches and then extrude this right the way through. We can go into our extent type and change that to all, and that will cut it the perfect dimension. Then next on, we'll make another sketch on that top plane, and we'll rotate it so it's a little easier to see. And this is where we can add in 2 circles, which will end up being our potentiometer holes. We need to add in 2 really small holes for our 3-point lever, and for our slot, we could just be adding in a center to center slot. And this can be about 45-degree angle going upwards, doesn't need to be anything too crazy. As far as all of our constraints that we want, we can add in some equals to these potentiometer holes and these mounting holes, and we can also say that there is a coincident relationship between the center line of our slot and these 2 endpoints. They line up nice and neatly. So within the sketch, we need to have a kind of anchor point. Where are all these values based off of? And so we may as well put in a midpoint right at that bottom edge of our bridge. There we go. And that way we can reference everything from that point. Importantly, we could be adding a horizontal constraint between that point and the very center of our rightmost circle. And we can also say that if you drew an imaginary line between these 2 points, or a construction line in our case, they would want to be parallel to the slot line as well. That'll line everything up much more neatly. And then for all the dimensions, you guys can grab it from our packet. All right, so with all of our dimensions in place, let's just quickly go over them. So we have this center construction line between our 2 potentiometer holes. That's going to be at a 45-degree angle. The center to center distance is 42 millimeters between some 7 millimeter diameter holes. The top one is located 42 millimeters to the left of that midpoint and 78 millimeters downwards. As far as our slots, like we said, the rightmost circle is exactly below this midpoint, and that would be 82 millimeters below. Both of our circles are 2 millimeters in diameter, and the width of our slot is also 2 millimeters as well. There is 6 millimeters between the center of the slot and the circles on both sides, and this slot has a center to center dimension of 29 millimeters. With that in place, let's go ahead and finish this sketch, and all of these profiles would like to be extruded all the way through our entire frame. So you can select the 5 profiles, pull that arrow downwards, and then select it to through all. So to make the cavity on the underside, I'm going to be making a new sketch on the bottom of our guitar. I'm going to be rotating it so it's a little bit easier to see. And this cavity really doesn't need to be any specific size or shape. As long as we can house all of our electronics and all of our wiring together, that's all we really need it to be. We could be making it using an offset and mirroring tool just so it looks kind of interesting, but there doesn't need to be anything complicated about this at all. Just a big old hole would work just fine. This is just a little extra. So let's start off by clicking O for offset, and I'm going to be selecting the outer profile, and I would like it to come in negative 20 millimeters. There we go. Then we can click our line tool, and I'm going to be making a totally horizontal construction line. I'm going to be selecting this and clicking X, and this will be a line that we can actually mirror this top profile around. It will give us kind of a pleasing teardrop shape. So let's use our mirror tool, select this outer profile as the object we would like to mirror, and then we want to select our construction line and click OK. Now you'll notice that this outer profile is still undefined because we really didn't say exactly where does this construction line live. I can move it up or down, it really doesn't matter. As long as this line passes just outside of all of our holes and it gives it just a little bit of breathing room, that's totally fine. We can click this and fix it so it's locked in place. Now we do want a little stepped feature inside this cavity so a plate can be rested onto it. So I'm going to be using another offset, something from the bottom that gives us about 5 millimeters. And annoyingly, you can't make an offset from an offset. So I'm just going to be adding 20 to 25, give us negative 25, and that's perfect. So for this project, we're going to be having 3 screws in all these corners that can hold down our backing plate comfortably. So I'm going to be making another totally horizontal construction line. So let's click X, that looks like it's at an angle, so let's change that to be totally horizontal. And this wants to be 80 millimeters long. Then I can use my construction line again, find the midpoint of that line, there we go, and then move upwards until I hit that inside section. And again, this is going to be another construction line. Then at all of these 3 points on here, I'm going to be making 2 circles on each point. These will be a 4 millimeter circle and then a 15 millimeter circle, and I'm going to be doing that on all 3 points. So we're going to be finishing this sketch and then extruding these circles down negative 15 millimeters. You can see the sketch kind of cuts them off, so we'll have to select 6 profiles for our 3 circles. This is going to be negative 15 millimeters downwards, but we also want to have a little bit of a step going downwards so that our backing plate can actually rest on top of it. So we'll be using another extrusion, and I'll be selecting this path right the way around it, including the circles as well, and this is going to be pulled down negative 3.2 millimeters. Negative 3.2. That's about 1/8 of an inch, which is a really common thickness for acrylic or something that you'd use as a backing plate for this. Then we can turn off our sketch and finally extrude this middle section negative 35 millimeters, which will leave us 10 millimeters from this bottom plane to the top of our guitar. And then the last profile that we'll be putting on this top face will be a little curved chamfer on top. Something a little bit more interesting, a little bit more tricky to work with. So let's make a new sketch on this top plane, and we're going to be using our 3-point arc. So we're going to be clicking 2 points on this curve, and you'll see that we'll be making our curve following the actual bowedness of this left-hand side of our guitar. This is going to be receiving a 300 millimeter radius, and if you draw a construction line from these 2 points, then that would be dimensioned to be 175 millimeters. You can see it really doesn't have any angle to it, which is why we're going to be saying that from the bottom of our bridge, our nice horizontal line, to there will be about 70 degrees. Then we'll be finishing this sketch and extruding down this profile negative 15 millimeters. Now we can add in our chamfer. Now instead of just a normal chamfer that we can put, if you look at the side profile, you can see that our height here is actually almost half of our length. So we're actually going to be needing to use a 2-distance chamfer. So go ahead and click our chamfer tool in our modify section, and under the type, change that from equal distance to 2 distance. and our chamfer is going to be living on this inside edge. Now our vertical height, that can be 15 millimeters, which is the same as our extrusion, but this length right here will need to be changed, and we want to get it as close as we can get to that edge, and this will take just a little bit of trial and error, because my numbers may be very different to yours, because it's based on the outside profile that we made during our fit point spline. Fit point splines are not a mathematical curve, they are purely artistic. So try to get it as close as you possibly can, go to like the 10th of a millimeter. So for me, it looks like 30.2 millimeters works about right, but as you can see, if I go to 30.3, I get a big ol' error. So go down to the 10th of a millimeter, that's gonna be just fine. It technically does leave us with this absolutely tiny microscopic little step. That's not an issue for us whatsoever. We can just click OK, and that is going to be the end of the CAD portion. Okay, so let's migrate from our design workspace all the way down to our manufacturing workspace. And this should be looking a little bit more familiar from our last project, but now we can go into much more in depth about how do we get our feeds and speeds, how do we actually put in multiple different setups, and how do we align all of the physical cutting operations to what we'd receive in real life, and how does that affect the order of operation for everything. For our project in real life, we'll want to do some of the cutting operations on top, flip our board over, re-bolt it down to our workspace, and then cut out all of our bottom features as well. So this is going to require two different setups where our origin is going to be in different locations as well. We're going to be grouping all of our operations, so we can start off with a top-down view of our board, make all of our cuts using the exact same cutter, our 1/4 inch end mill that we made in the last class, do them back to back to back to back to back, then switch over to a drill bit to cut out some of the more important features in there, then flip our board over, change out to a different drill bit, cut out the rest of the features on the underside, then flip back to the 1/4 inch end mill and complete the entire project. So you'll notice that we'll have a top section and all of the tool cuts, and then a bottom section and all of the cuts for that. And we're going to be working with the mindset that when we rotate and re-secure down on board, that it is exactly in the right location. A lot of people will put different dowels or different registration pips so their board is exactly in the right rotate or in the right location, just reverse. Some people have different squares already built into their CNC so they can push it up against a frame. We're going to be skipping all of those and just assuming that we can rotate and bolt it and it be in the perfect location. So just like we did for our longboard project, we want to go to our browser and change our units from millimeters over to inches, because all of our tools and bits are going to be in using imperial and fractional units. And we can start off by going into our setup menu, selecting new setup, and this will make that yellow stock box that goes all the way around our piece. Now for our stock origin point, we always want to put that in the front top left location, because all of our cuts are going to be based on the top surface of our piece. For example, the holes for our pickups, I don't really care about the underside of my piece, because I'm saying I'm cutting in a certain amount from this top surface. We can also go into our stock tab and get a top-down view, and it's always set to relative size box, and we're going to be keeping that. Because we've got a slightly larger project, we want our frame or our leftover material to be larger as well. We're going to be cutting everything out with a 1/4 inch end mill, and we want to be adding on 1/4 and then a 1/2 inch on either side for that leftover material. That would be added up to a total of 1.5 inches extra on all of our sides. So let's go into stock side offset, change that to 1.5 inches, and our top offset, we're going to keep that as 0. We're assuming that our wooden board is already the right thickness. Then we can click OK, and then go into our browser, double click this, and we'll rename this as top. So in our previous class, we talked about feeds and speeds just a little bit, but we didn't talk about how you can actually calculate it. Because I have my own set of tools, but what if you buy a brand new set of tools? How fast should you be running this? Because if you run it too fast, you're going to be breaking your bit. If you run it too slow, then you can't get material out fast enough. You'll end up burning the material, which heats up your bit and then breaks it. So you've got breaking on both sides of the spectrum, but there is a middle sweet point where we can run the machine fast enough where it is efficient time-wise, but it isn't so slow that you're actually going to be, well, wasting time. So let's go over the math real quick. So we're going to be working on speeds and feeds in a very basic sense. The speed is what is the rotation, the RPM, and then the feed is exactly how fast is your tool moving linearly. The speed calculation is very easy. You're going to be taking the material's surface feet per minute, multiplying it by a constant 3.82, and then dividing the whole thing by your tool's diameter. Now the surface feet per minute is a strange value of just how tough is your material. If you have something like cold rolled steel, which is incredibly strong, then that's going to require a lower number, something like 40 to 60. If you have wood, well, this is going to be really easy to cut through, so you can have a number up to 1500, and every material in between is going to have its own specific number. Then you're going to be multiplying that by 3.82, that is just a conversion between our circumference to our diameter from feet and inches, and then we'll be dividing it by our tool's diameter. So for our project where we're going to be cutting soft wood, so 1500, multiplying that by 3.82 and then dividing it by a 1/4 inch diameter end mill, that will give us a pretty good, really fast RPM of about 23,000 RPM. Most CNC routers have a high max of 25,000 RPM and a low RPM of 5,000, so we're right near the very, very top of this. And then to calculate our feed rate, we need a slightly more strange formula. Our feed rate is going to be measured in inches per minute, and this is going to be a multiplication of our speed, our chip load, our number of flutes, and our depth modifier. Now the speed you can get from the other formula is going to be multiplied by our chip load. Now a chip load is literally the size of a chip that is removed from one tooth of our piece. You can find really large spreadsheets where it'll say, oh, well, I'm cutting with a 1/4 inch diameter end mill into soft material, and it's going to give me a rough gauge between 7/1000 of an inch and 9/1000 of an inch. We're going to split the difference and multiply it by 0.008 inches. Then we'll be multiplying it by the amount of flutes on our tool. Usually a lot of tools like end mills will have 2 flutes, that's the grooves you'll have on the side, same amount you'll find on a drill bit. On end mills you can also get 2, 3, 4, 6, 8, 12, really as many flutes as you'd like. The more flutes you have, it means the more material you can remove per revolution, but it means the tool is more expensive. And then you'll be multiplying all of that by your depth modifier, or the ratio of how deep are you cutting to the diameter. If you're just cutting with a 1/4 inch end mill and you want to cut in a 1/4 of an inch, then your depth modifier is 1. If you're going to be cutting in 1/2 an inch with the same tool, then your depth modifier is 2. Cutting in 3/4 of an inch with a 1/4 inch end mill, they'll give you a depth modifier of 3. This will slow down your feed speed, but it will also cut away more material. We're going to be taking it nice and light for our feed rates, so we'll be multiplying the speed, which would be 23,000 RPM, multiplied by our chip load, which is 8/1000 of an inch, multiplied by 2 flutes and a 1/4 inch of depth, so 1 modifier, or 1 depth modifier, which will give us a feed rate of 368 inches per minute. So for this project, we are going to be using 2 different size end mills. We're going to be using our 1/4 inch end mill, which is our bread and butter, and I want you guys to make a 3/32 inch end mill. You guys can find all the dimensions in your packet, but I want you guys to calculate all the feeds and speeds for this bit. So we'll be starting off with our first operation of 13 to be cutting out the contour of our entire guitar. Now this is a really thick project, and cutting it all in one go, that's going to be a little tricky with a tool that's not tremendously long. So what we'll do instead is actually only cut half of our thickness, leave in some tabs, and then for our last operation, flip it over and cut it from the other side so our tabs are still holding in place. So we'll be using our 2D contour tool for this. And just like before, we're going to be selecting the bottom edge of this. Our tool is going to be our 1/4 inch end mill that you guys can grab in your custom tools. We'll select that. And everything else should be pretty normal. We are going to be having in some tabs, let's say 4 inches of spacing, just so we've got some good holding power. For our heights, this is where we'll be needing to have our bottom be set to only half of our thickness. So if you go into your dialog box, you can see the bottom height is selected, and we want to be changing that from the model bottom. You can see that blue line jumped up right there. And then the offset, we want it to be halfway up. So we know the thickness of our piece is 45 millimeters, but this is reading it in inches. So I need to do our unit conversion. So I'm going to be dividing it by 25.4 and then dividing that by 2. There you can see we've put our blue line right down the middle. Then we'll be going up to our passes, where we can reduce our tolerance from 40 thousandths of an inch down to 4 thousandths of an inch, make it a little bit faster for our CNC to cut this. Then for our sideways compensation, I'm going to be changing this from a left direction to a right direction. This will give us what's called a climbing cut, and it will give us a slightly better surface finish. Then we can go down to multiple depths. Because we designed everything as far as our speeds and feeds around 1/4 inch of depth, then I wanted to change this maximum roughing step down from 0.75 to 0.25. If you wanted to keep that as 0.75, that's fine, but then it means you need to change around your feeds to adjust for that 3 depth modifier now. And then in our linking stage, remember the safe distance, we really don't need to worry about that too much, but we do want to have a ramping operation, and then we can click OK and then discard that warning. This will give us a few paths that cut right the way through. You can run through the simulation and check it out if you'd like, but we're going to be passing on to our next operation. For our next operation, we'll want to be clearing out this cavity for the neck and then the 2 pickup slots. So we're going to be using a 2D tool known as 2D Pocket. This is a really great tool if you've got some kind of complicated geometry that you just kind of want to gouge away. Sometimes it's called hogging material. So let's select 2D Pocket. For our tool, again, we're going to be using our 1/4 inch end mill. For our geometry, we actually want to select this bottom faces, that one, and that one. For our heights, we really don't need to mess around with whatsoever because we're just saying, hey, cut all the way down to that surface. For the passes, again, we do want to have a right compensation. You're going to be having that on basically all of your CNC routing operations. Again, our multiple depths, we want to change this from 0.025 up to 0.25. And then you can see on the very bottom, we also have a stock to leave section. This is set to leave 2/100th of an inch. I don't need that. This can be a final operation. Generally, Pocket is used for a roughing operation, and then you go back and clear that really small 2/100th of an inch with a little bit more of a detailed pass. We don't care about that. These are never going to be seen. They're going to be covered with other components that live on top of it. So we'll just say, hey, clear it all the way out. And then our linking operation, again, we can put in some ramps if you'd like. This will put in a helix operation. So it's going to be corkscrewing down, clearing 1/4 inch of surface, screwing down a little bit further, clearing that out until it gets to the bottom depth. That's all good. We can just click OK and ignore that warning. Again, as you can see, we have got these little red spirals all the way through. That's what the tool is going to be carving down, and then multiple depths of operations. If you guys ever want to see exactly how long this machining time will take without having to do a simulation, you can just go over to your browser, right click it, and then select machining time. That will give you a little pop-up. That'll say for these 3 cavities, that'll take about 5 minutes, so not too long. And we can just click close. To carve out the slot, just like the outer contour, we actually only want to cut halfway through, flip it over, and then do the other half, and that will require a little bit of a mixture between the 2D contour and the pocket. We're going to be using a pocket just to gouge away all the material because I don't care what's on the inside, but I only want it to go halfway through. So again, let's go into 2D, select 2D Pocket. This time I want to select the bottom edge as our geometry to cut through. Again, we'll still have our 1/4 inch end mill. During the heights, we want to set the bottom height to be the stock bottom. And then we want our offset, just like the contour, to be 45 millimeters divided by 25.4, which makes it into the inches, and then divide that by 2. And if you look at the sideways, you should see this blue line that denotes the bottom section that it'll go to. Then for the passes, again, change this over to right. We do want to have multiple depths, and we do want to have our ramping going all the way through. That looks great. Nice and quick one. And during the simulation, as you can see, does leave us with that bottom section right there that we can then cut through on the underside. And then the last operation that we'll be doing with our 1/4" end mill will be taking care of this angled chamfer. This is going to be kind of tricky because not only do we need to use 2D tools, but we also need to do 3D tools. And we're actually going to be using 2 different passes for this. We're going to be doing a roughing pass and then a parallel pass just to clean up the rest of the material. If you go at this with just one gigantic cut all the way through, you'll end up putting so much stress on your cutter that it'll actually snap off and break. And that's going to be a bit of a nightmare. So we'll be doing 2 different operations. So go into your 3D section and we'll be using a 3D pocket clearing. This will do a similar thing where it actually steps down layer by layer, then we can do our final cutting. So select pocket clearing. Again, we'll still have our 1/4" end mill, but for our geometry, instead of our bounding box, we actually want to make some selections. So we want to select this top edge and this bottom edge. And that'll kind of define, well, this inner edge that will be, or this inner curved surface that we want to be working on. We can check the model section, and this is saying, okay, well, within these 2 bounds, what is the surface you're clearing? And that's going to be this face right there. Then going through all the normal stuff, heights, we don't need to mess around with it. The passes, really don't need to mess around with it as well. The stock to leave, we can actually reduce this down to 0, or you can leave it on. It doesn't really matter because this is purely a roughing phase. The second operation that we'll do will clear the rest of the material either, so it doesn't really matter too much. And then for the linking, again, we don't really need to mess with this too much. When we click OK, you guys can actually see that it will do quite a lot of steps through this. So if you look at this simulation, you can actually see that we've got a ton of blue lines going all the way down. And this is essentially every single step that it's going through. This is going to take a lot of time, and for a roughing pass, that's completely not necessary. So let's edit that. So let's go back into our browser. I'm going to be right-clicking the 3D pocket, go up to Edit. Now when I see the multiple steps that go into making all of these cam operations, that kind of leads me to think about the passes section. And you can see the maximum roughing step down, which is exactly how far is that bit going down per pass, is set to 0.025. That's a lot. If we're cutting down maybe an inch, that's a huge amount of steps. So let's change that over to 0.1 inches. And if we click OK, there we go. Now we see still the kind of ramped or the stepping profile of this is being cut out, but it's going to be taking vastly less amount of time. Now that was the roughing operation for this, so let's put in a finishing operation so it can make it a little bit nicer. Normally this would be done with a bull nose bit, so the radius of that end mill will actually give you a little bit more of a smooth curved surface. For us, if I'm imagining I'm manufacturing this, I'm never going to be done with it unless I sand it. So if I have a slightly rough surface from the parallel tool that will be used to make this finishing pass, that's fine by me. I'm going to be sanding it regardless. I just want to get rid of those really large, big stepping features. So let's go into our 3D tool, and I'm going to be selecting parallel. That's my go-to tool anytime I'm doing any smoothing passes. So just like before, we're going to be keeping that 1/4" end mill just for kind of ease of use. For the geometry, we're going to be doing the same thing that we did for the 3D pocket. So I'm going to be selecting the top and bottom edge that define our 3D curve. Then for our model, I want to select that chamfered surface. There we go. For our height, don't need to mess with that too much. And for our passes and linking, I also really don't need to worry about that too much because this already assumes that I want a really clean surface with lots and lots and lots of step backs, which will give me a good surface. The stock settings in this are shockingly quite good, so I'm just going to be clicking OK and not mess with it at all. And you can see we have got a lot of lines of this, which is good because this is a finishing pass. So if we take a look at how long this operation will do, even though it's not taking off that much material, it will actually only take 32 seconds to machine this entire parallel. So with that operation, we are now done with our 1/4 inch end mill, and we now need to make a new 3/32 inch end mill. So again, I'm going to be going into my tool library under the manage menu, into my custom tools, and this is where I'm going to be adding on a new flat end mill. So this cutter can be called a 3/32 inch end mill, and you guys can find all of the dimensions for this cutter in our packet. As soon as you're done entering in all the dimensions, go ahead and go into the cutting data, where I want you guys to do the math for all of the speeds and the feeds. So with this all done, we can close this down, and then using our drilling tool, we can be selecting our 3/32 inch bit to be cutting out our 6 holes up top, and then our 2 on either side of the slot. So go to your dialog box and change this from a 1/4 inch tool, and instead of using our 3/16 inch from the other operation, we're going to be checking the milling and selecting our 3/32 inch bit. And by selecting this, we are going to be using it on these 6 holes up on top, and then our 2 holes on the bottom. Don't need to worry about the slot, we'll do that in our next operation. The reason that we can do this with our 3/32 inch end mill and we don't need a separate drill bit is because if you look at the underside of a lot of drill bits, the blades go right the way to the center. If you have an end mill where there's a little circle on the very bottom, it means it can cut linearly, but it cannot plunge. That's the difference that we're working with. And then all of the rest of the tabs in here, these can be kept absolutely the same. And with that same tool, we're going to be carving out this slot. So go into your 2D menu, and you can see we actually do already have a slot tool. And you want to be getting your camera straight the way down so you can select that bottom edge of our slot. Again, your tool should be that 3/32 inch end mill. For our height, we just want it to go all the way through. That's why we selected that bottom edge. For our passes, because this is a pretty skinny bit that's very likely to break, when you check multiple depths, it'll be 0.04, which is about 1 millimeter, which is about half the diameter of this bit. I know this will take a longer amount of time to do, and I could push this bit to its absolute limit, but I would much rather stay on the more careful side and say, yep, that's fine. It's only one slot, so it's only going to take a few extra seconds, but I'd much rather go at a much lighter pass than go really heavy and, well, end up snapping my tool, which would be a disaster. All of our linking looks perfectly fine, so let's click OK. And then you can see we've got a lot of different steps on this, but that's going to be just fine because we know we can carve out this cavity safely. So with that operation done, we can now call all of the operations for our top completely done. Now we're going to be making a second setup on the underside of our piece. So go ahead and rotate this so it's a similar view but on the very bottom, and we're going to be making a new setup. This one, just like the other one, is going to be the exact same size. We can actually say from the preceding setup, so it doesn't need to add in the 1.5 or anything like that. It's already done. What does need to happen is we want to say that the stock point is again in that front left top corner, but all of our arrows are actually going the wrong direction. So that's why you need to go into the work coordinate system and actually change this around. This can be slightly tricky and kind of annoying to get right, but we want to say that our z-axis is pointing up, our x-axis is pointing to the right, and our green axis is pointing away from us. If you wanted to, you could just click all of the arrows until it's kind of already in the right orientation, or you could go through and set this to z-axis and x-axis, and then click all of the axes in the origin so they're all pointing the right direction. It's a little tricky, but you guys can absolutely do it. So we'll close that down by clicking OK, and now our first operation on the bottom is going to be a drilling operation. Now this is going to be using a tool that we actually don't need to make because it's actually already in the Fusion library, which is always nice. So let's select on the new tool, and we can go and highlight the Fusion 360 library. And it's saying, okay, what do you want? We want a 5/32 of an inch, which is the closest to 4 millimeter holes for our 3 holes in our back cavity and the 4 holes in the neck. So we can check out our tool category. It's already set to hole making. I don't really care about all of these. I guess a drill would be best. but it's our diameter that's most important. So I'm going to say 5 divided by 32, and it should only have one bit, which is right here. And I can just say, yep, that's the exact tool that I want. For all of my geometries, I would like to select these 4 holes and the 3 holes on the back of our cavities. Perfect. Then just like before, the heights, really don't need to mess with that too much. I do want to go into the bottom height and say drill the tip through the bottom. This is the same issue that we had with our longboard class, where it wasn't going all the way through. And in our cycle, it's saying, yep, drill in and then drill out as quick as you can, just to get those chips out of the way so you don't cause a fire. That looks perfect, so we can click OK. We'll finish off the other side of the bridge slot by going into 2D pocket. This time we're going to be selecting the bottom edge from the bottom view, which is technically the top edge. Don't worry about all that. We're going to be switching over again back to our 1/4 inch end mill tool for the last time. So 1/4 inch end mill, let's select that. All of our feed and speeds already built in, that's what we like. The geometry, that's already selected. The heights, again, we've already cut in half of it from the underside. So I'm going to be saying from the stock bottom, we want to have an offset of 45 millimeters divided by 25.4 and then divided by 2. That'll put that blue line again right in the very, very middle. Perfect. Then for our passes, we want to go on the right hand side. We want multiple depths that are 1/4 inch in depth each time, and I don't want to leave any material this time. I want it to cut all the way through. Then for our linking, we can leave all of this just the same and click OK and get rid of that warning tool as well that we all hate. So there we go. It will cut all the way through, and this little green area, when we do our simulation, that's not even going to be there. Then moving over, we can get rid of the cavities in our back section. This is going to be with a 2D pocket tool again. Let's clear out this little step first. Again, with our 1/4 inch end mill, I'm going to be selecting this bottom surface here. I would like to do this by not changing the height, but by having multiple depths. Technically, because this is less than 1/4 inch of depth, it can just do it on one pass, no problem. In the linking, I can leave that all the same again. Click OK, and then adding in another 2D pocket, but now for this bottom section, with all of the exact same tools and all the exact same features as well. No problem there. Multiple depths of 1/4 inch, so that we're not wasting time, because this is a very, very large cavity below. That looks perfect. There we are. So now we can hog out a lot of material there. That's going to take a little while, probably the longest amount of time to carve through all of it, but that's okay. This is a total going to be much less time than if you had to carve this out by hand. And then as our final operation for this entire project, I would like to cut out the outer contour, but this time to the other half depth. Because remember, the first operation that we did only carved it out to half of the depth and left some tabs, so this will now cut down to the underside of those tabs, so they still should be left. So let's finish it off. 2D contour. This time, instead of selecting the bottom edge, because our bottom edge actually gets cut in with our little chamfer, we're going to be selecting the top right there. Again, we still got our 1/4 inch end mill. For our heights on here, we actually still want to be selecting the model bottom, but still 45 divided by 25.4 divided by 2. For the passes, we still want to have multiple depths, this time in 0.25, but during our linking, we still want to have ramping. I just want to double check. Yep, it does not have tabs selected. We already have tabs from the other project. Totally not needed. So let's click OK and get rid of all of those. Perfect, and that is going to be it for all of our operations. All right, so now let's go into a simulation to see exactly how everything looks. So let's simulate this, and it's going to be going from one tool to another instantaneously. Again, it always speeds up just way too much for me. So let's just click play, and we'll start off with the 2D contour. We can speed up just a little bit. It's going to be ramping downwards, cutting 1/4 of depth and then stepping down again, carving all the way around. Again, if you don't want to see this transparent stock, you can always change around all of your settings in all of the settings over here. It will be carving out until it gets to that next stage. There we are. Where it's going to be carving out the pocket. The pocket of the neck is going to be first. As you can see, it actually follows the contours quite nicely of all of the features that we have around there. And then it's going to be moving on to the pockets that we have for the pickups that we have. We've got 2 of them in there. So carving that out, carving that out, carving that out, all of the multiple depths. If you ever want to fast forward to the next step, you can just click next operation. This one is going to be going down to halfway of the bridge, and then it's going to be moving on to starting the roughing portion of the angled chamfer right there. Then it's going to be moving into the parallel. This is very jerky, it's going to be going back and forth, not taking off too much material, but kind of defining that slope. Then it's going to be drilling out all of our 6 holes. Let's go back to a model view where it can then carve out all of this slot section right there. Then we can go over to our underside where we can run another simulation and check out what it's going to do. All 7 holes that we have on there, then flicking over to the bridge to carve that out as a final operation. Then moving over to this little step feature and then the larger pocket. Then it will be carving out the entire profile and everything should be done. And as our last step, we do need to export all of our files, and this is where we can actually make it a little bit more efficient. In the longboard section, we had 3 operations with 3 different tools. For us, we've got a lot of operations that we group together by tool. For example, starting with the 2D contour, we actually used the exact same tool up until the parallel. So I'm going to be highlighting all of them and then going and post-processing it in one big go. So we can call this number 1, 1.4 for a 1/4 inch end mill, and then we always want to export it in units of millimeters. So go ahead and make a new exported post-processed file for every single operation that we have for the top and for the bottom using the same tool. And that's going to be it, guys. So go ahead and try and find a CNC and get running.